did the introductions and thanked the premier of China, Jiang, for coming. But what the head of the International Mathematics Union did to the name of the premier had about half the audience laughing. It was just embarrassing. So I hope not to do that. Wow. Okay. Very good. Very good. So what's it like at the Chennai Mathematical Institute? That sounds like a...
Life is, well, it's all online actually, because I spend part of my time in Pondicherry and partly in Chennai. And right now I'm in Pondicherry because this particular semester I don't have any classes, so I enjoy staying at Pondicherry. I like to be here. And once the classes start, I guess I have to go back to Chennai. But activity in the institute is rather curtailed, I think, because of all these things. But there's a slow incoming of students now. I think there's some sort of I think they have some sort of a routine by which partly the number of students are getting allowed here because room sharing is a problem in the hostels. So I think people will be allowed for some time and then they have to go back and then somebody else will come in. It's like blocks coming in together. And so it's a strange arrangement which is happening. Let's see how it goes. But classes, I think, will continue to be online for some more time because most of the building is air conditioned and the lecture rooms, and they have been designed for that. So if you have a large class with no air conditioning, then that could be rather difficult for the speaker and the audience. And COVID, I think it's not safe to have air conditioning there.
So that was an issue. They were thinking of putting regular windows into our classrooms, and that was an idea, but it never eventuated. So, okay. Well, I think it's almost time to start. Professor Cannon, do you want to introduce the distinguished...
One little announcement. This talk is going to be a little longer. It's like 90 minutes, right?
I've planned it for 1 hour, but I could extend it if you... it depends on the audience. I can go on endlessly.
Okay.
Yeah, it's...
Dr. Suratno, to introduce the speaker, I'm not readily having all the details.
So let me introduce. Firstly, I want to say this is our first in the Mathematics Department Distinguished Lectures series. My name is Jesse Deutsch, and I'm at SRM University AP. And the Distinguished Lecture Series are lectures by invitation only to high-ranking mathematicians of notable achievements. Okay, and I'd like to introduce our first speaker, Professor Vikraman Balaji, who has quite a background. He's at the Chennai Mathematics Institute, and he's won the prestigious Shanti Swarapatnagar Award. He was awarded a J.C. Bose Fellowship. He is a Fellow of the Indian Academy of Sciences and a Fellow of the Indian National Science Academy. And he's an elected member of the National Academy of Sciences, India. He is going to be talking on the Narasimhan-Seshadri theorem and some ramifications. So without further ado, we would like to hand the floor over to Professor Balaji, and we eagerly await your discussion and your talk.
So, thank you very much for the kind introduction. It's a pleasure to give this talk, especially because one of my own younger colleagues is also part of the faculty, and I was responsible for sending him there. And so it's a great pleasure to give a talk on Narasimhan-Seshadri theorem. Also, perhaps it's in some sense opportune or maybe appropriate in some sense because last year in July, Professor Seshadri passed away, and this year in May, Professor Narasimhan passed away. Both of them were born in 1932, within a few months of each other. And so I thought I should start this lecture by giving a few minutes about what their personalities and where they did their education, so that some of the audience who may not know about it would also know about this. I've given a few talks about Seshadri's work. So let me just say that both Narasimhan and Seshadri come from southern part of India, basically Tamil Nadu, where from small time towns. Seshadri is from Chengalpet and Narasimhan is even from a much smaller place, I'm told. They used to travel, Narasimhan at least used to travel long distances to go to school. Seshadri's family was a little more affluent. It was, I think, a lawyer family. So Chengalpet was already reasonably developed. So they had decent schooling there. And they both, had, it looks, deep interest in mathematics during the school times, but the mathematics which is taught in school is of a different kind altogether. So they both landed in the Loyola College. In those days, it was the prime place for doing mathematics in India and in Chennai, apart from two other places, which was the Presidency College and the Madras Christian College. So Loyola College had a distinguished mathematician by name Father Racine, who himself was a doctoral student of Elie Cartan from Paris. And therefore, he was aware of the modern developments of mathematics. Narasimhan and Seshadri did their bachelor's honors in the Loyola College, and both, advised by Father Racine, went to the newly formed Tata Institute. This was in 1953. Both joined together there. Although they were in the same class, I believe they were not, in the same friends group till they reached the Tata Institute in Bombay. And there, these two, along with maybe one or two others, had joined the early batches of the research program there, which was started by Professor K. Chandrasekharan and K. G. Ramanathan, both again from the Madras University in those days. And so the Tata Institute had taken on itself the role of introducing young mathematicians to modern mathematics in their sense of modern mathematics, because mathematics pre-independence was essentially dominated by Ramanujan's genius, and some other aspects of modern mathematics was introduced in Madras University by Professor R. Vaidyanatha Swami, where he took the initiative of introducing geometry, logic, topology, and other things to students, and students did develop on those fronts as well. But the influence of number theory was very strong, and so that was predominantly the branch in those days, where Ramanujan's influence was very strongly felt. When Narasimhan and Seshadri came to the Tata Institute, Professor Chandrasekharan had a very good rapport with the French School of Mathematics, and several visitors from France, like Laurent Schwartz, Elie Cartan, and all these people, they used to come regularly to the Tata Institute, and this was the atmosphere in which they both developed. They both went to Paris almost at the same time after finishing their PhD, and both kind of developed somewhat different strengths in Paris. Seshadri was more algebra geometric, and Narasimhan more towards partial differential equations and geometry from that direction. But as things would have it, when they came back to India in 1960, I believe, both, they were the early leaders of Indian mathematics. Seshadri had made a name for himself in Paris by proving this Serre conjecture, and he was working with Chevalier on Picard varieties and many aspects of mathematics, which was influenced largely by the Bourbaki school. And the prominent people at that time in Paris were the seniors like Chevalier, Cartan, Schwartz, and others, but also the young geniuses like Serre, Grothendieck, and that school. And Grothendieck's influence was gradually growing into great proportions there. And when Narasimhan and Seshadri came back in around 1964, I think Seshadri's thesis was somewhat connected to vector bundles again on the projective line. And he, in fact, gave a proof of what is now called the Grothendieck theorem for vector bundles on the projective line, and using what is called the Birkhoff approach by proving it's a direct sum of line bundles. Grothendieck, of course, proved it for all principal bundles, which is a little more subtle. And Seshadri, therefore, was aware of vector bundles. So I think in 1964 or 65, around that time, Narasimhan and Seshadri came together to address certain questions that Andre Weil had posed in his paper. It will come in my work, in my talk today. So this was the origin of the Narasimhan-Seshadri theorem, which was proved sometime in 1965. And their influence on Indian mathematics was very, very strong. They built the school almost single-handedly. Most of the second generation after them were either Narasimhan students or Seshadri students who have prospered very well. And Seshadri came to Chennai in 1984. Towards the end of 1984, I joined him as a PhD student. So that's my association with him for several years now. So it's a privilege and a pleasure to talk about the Narasimhan-Seshadri and some ramifications. The ramifications part was intended to be a pun, and I do hope to perhaps indulge in that pun towards the end of my talk. But let me begin by telling what is some sort of a broad motivation. Since I mentioned Andre Weil's name here and his paper called the Généralisation des fonctions abéliennes, he was interested in generalizing the theory of abelian functions, Kummer theory, and such things to non-abelian situations. And this is how he came to that paper in 1938. It's a very beautiful, really non-trivial paper in many ways, with interesting ideas. That was the starting point of the Narasimhan-Seshadri theorem and its philosophy. Although there are some interesting connections with, let me just see. Yeah, with the uniformization theorem. So I'm going to start with a single quote from a letter of Andre Weil to his sister Simone Weil, written sometime in the late 40s. And this is about searching for analogies. So searching for analogies, which is seldom manifest, has been a fruitful, even indispensable source of discoveries in all of science, more so in mathematics. The analogies between fields of algebraic numbers and the fields of algebraic functions is a heuristic principle which guided most of the fundamental discoveries in the 19th and 20th centuries. So here Andre Weil speaks about this triangle of Riemann surfaces, curves over finite fields and algebraic numbers, which he likens to a trilingual inscription, something like the Rosetta Stone analog. That's what he calls it, where you have the same statement written in 3 different languages, and that's how the deciphering of the hieroglyphics took place. So this is like a trilingual inscription that tells us about the same thing in different ways, with indecipherable and ruined fragments in different places in parallel texts. So he likened the study of Kummer theory and algebraic functions to this kind of a philosophy. And somewhere when I read it, I found that the Narasimhan-Seshadri theorem, or theory as I would call it now, gives something like a trilingual inscription or a philosophy, which I'll try to give some sort of a feeling for it. Okay, so this is the references in the notices of AMS. Andre Weil's letter to Simone Weil is published there, Analogy in Mathematics. But I was privately told that Andre Weil actually wrote this letter to another mathematician, but put the address as his sister Simone Weil to disguise it in those. I don't know why. I mean, could have been during the war. Anyway, so let me begin. I mean, the talk is, as I said, it's highly Bourbaki influenced mathematics, but it's beautiful mathematics in my sense. So it's somewhat sophisticated. So let me begin by saying that so I'm going to assume a little bit of classical compact Riemann surface theory. I'll try to tell whatever I can during the lecture. So let X be a compact Riemann surface of genus G greater than or equal to 2. So a compact Riemann surface should be thought of as a real orientable 2-manifold, which is topologically a sphere with G handles attached, where G is the genus. And in this case, I'm assuming G to be bigger than or equal to 2. In the so-called classification of compact Riemann surfaces, the Riemann sphere is the genus 0 object, and the elliptic curve, which is the complex plane modulo lattice, is the genus 1 object. And those two by the so-called uniformization theorem, have different universal covers. The sphere is simply connected, and the elliptic curve has the complex plane as a universal cover. When the Riemann surface becomes genus bigger than or equal to 2, the universal cover is uniform. This is something like the general type scenario. The universal cover in that case is the upper half space. And the so-called fundamental group of the Riemann surface acts on the upper half space. So the fundamental group of the Riemann surface is a free group on 2G letters. So the 2G letters I denote them by A1, A2, AG, and B1, B2, BG, modulo a single relation that the product of their commutators. When I write bracket AI, BI, it means AI, BI, AI inverse, BI inverse. I want the product of all these. That's the only, in a free group, there are no relations between among the generators. I add one such relation. One relation is that whenever I have AI, B, A, B, A inverse, B inverse, I should put it equal to 1. That's the only relation. That means I want the A, B to be equal to BA with the ordering. I mean, it's not for across the ordering. I want A1, B1 to be equal to B1, A1. That's the only relation I'm putting for all A2, B2 equal to B2, A2, like that for all the G of them. So as I said, the universal cover is what is called the universal cover. It's a simply connected cover for the Riemann surface with the fundamental group as a group of covering transformations or the group of deck transformations. The fundamental group will act freely on the upper half space, and the quotient is the Riemann surface X. Of course, in the Narasimhan-Seshadri theorem and its ramifications, one would encounter more general Fuchsian groups, which are discrete subgroups of the automorphism group of the upper half space. And I will come to them a little later towards the end of my talk, where other Fuchsian groups. The fundamental group is an example of a Fuchsian group, which is acting freely. The other Fuchsian groups could act with so-called parabolic, elliptic, or other fixed points. Each one is classified by a certain type of, the automorphism group of the upper half space is PSL2R, and your groups, Fuchsian groups can be described in terms of what sort of matrix decomposition is there in terms of the Jordan holder, sorry, the Jordan canonical form for the matrices. So I'll come back to these Fuchsian groups a little later. So what is the broad aim? I mean, the question that Andre Weil was interested in, which Narasimhan-Seshadri theory would do, its aim is to classify what are called holomorphic vector bundles on the Riemann surface X. A vector bundle, I mean, when we talk about a compact Riemann surface here, one of the things that one should remember is that a compact Riemann surface is a compact complex manifold. Therefore, this so-called maximum modulus principle would tell you that you can't really have any global functions, holomorphic functions on X. They're all constants. So, and without having a good space of functions on a space, we can't understand the space. So the natural thing to look at is what comes up in the theory of bundles, that you should look at what are called line bundles or vector bundles, where a line bundle is a construct on top of the Riemann surface X, where each fiber is a complex line, but so it's like a space L to X. The morphism says that the fibers are all the complex lines, and this is locally trivial. That means there is a covering for the base X, say some open subsets UI, which are like small disks in the Riemann surface, so that on those disks, the line bundle looks like the complex line C cross UI. It's trivial in that sense. Okay, so there's this problem about giving a slide talk is I can't write, and that is really a problem. Okay, so therefore, a line bundle in some sense is the complex line over C glued up. Although it looks like fibers look like C, the fibers are in some sense varying, and the functions on the Riemann surface is replaced by what are called sections of this line bundle, which is the correct analog of functions. And studying the space of sections was already done by Riemann and the so-called Riemann-Roch theorem, in fact, tries to understand not only the space of sections of line bundles, but even the so-called cohomologies of these line bundles. So we are interested in classifying holomorphic vector bundle. The vector bundle is a little more general. It's just that the fibers are no longer the complex line, but the complex vector space Cn along each fiber. But the vector bundle is not a product. It's not a product of Cn cross X. It's locally a product, but glued together with transition functions. Now, the so-called Jacobian variety of a Riemann surface is a basic structure here. I mean, when I'm looking at classification of holomorphic vector bundles, we should first classify holomorphic line bundles as line bundles. Fibers should be one-dimensional, complex. Holomorphic means that the transition functions are holomorphic functions from the intersection of these, I mean, ui intersection uj to the automorphism of the fibers, which is in this case either GLN for the vector bundle of rank n, where rank is the dimension of the fiber, or a GL1, which is a C star in the case of a line bundle. So the transition functions are written as GIJs from ui intersection uj to C star, and they should satisfy the so-called co-cycle conditions. And notice that since C star is an abelian group, we are still in the so-called abelian situation. The moment you go to a vector bundle, that group becomes non-abelian, and we enter the non-abelian framework. So the Narasimhan-Seshadri theorem is a non-abelian framework. The Jacobian that I'm going to talk about for a little while is the classical abelian situation. The Jacobian variety of the Riemann surface gives a geometric structure to the space of isomorphism classes of line bundles of a fixed degree. So I have to tell you what the degree of a line bundle is. So I'll just mention these things. Unfortunately, this is a little technical, but I have to build these things as a part of my language. Otherwise, I would require more a course for this kind of thing. Isomorphisms of line bundles can be easily defined. And there's a natural way of defining isomorphisms. And what is the degree of a line bundle? It's a topological invariant. You know, we are talking about holomorphic structures here. So a holomorphic structure means that I have some underlying topological object, and I'm giving a complex structure to that. Okay. So the degree is, the genus is, for example, a topological invariant for the underlying topological surface underlying the Riemann surface. So the genus is a topological invariant. And so when I talk about line bundles now, I have something called the degree, which is defined in terms of the so-called Chern class. It's the first Chern class, or the degree of the line bundle. And I'll explain it a little bit, but not too much. But as we go ahead, I'll tell you exactly what it is. So one can similarly define the degree of a vector bundle. That is, if you take a vector bundle which is of rank n, then there's something called the top exterior. I mean, it's like a linear algebra construction. You can take the top exterior of the vector bundle, and that becomes a line bundle. And you can take the degree of that line bundle, and that's called the degree of a vector bundle. So these are the basic, I mean, I'm building the language to be able to talk about some of these things. So as continuous vector bundle, that means if I'm not thinking of holomorphic vector bundle, but just as topological vector bundles, the rank and degree of the bundle in some sense is a complete information. If the rank and degree are the same, then I mean, you more or less can classify the bundles. They are those two invariants classify the bundles in the continuous category. So we fix those invariants and then try to see how to put holomorphic structures on them, and then to classify the holomorphic structures on line bundles or vector bundles of fixed rank and degree. That's the philosophy. That's the kind of question that the Jacobian variety addresses. So as I said, the Jacobian JX, which is also called the Picard variety of line bundles, there are different aspects, as we'll see, is the isomorphism class of line bundles of degree 0. So here, when I said, I mean, there's something called the degree 0. I'll write the right kind of exact sequences to see what do you mean by degree 0 here. These are intrinsically defined on the curve. I mean, all these whatever I'm talking about. But there's another way of looking at them, which is called you can look at the so-called divisors. A divisor is like a free group generated by the points of the Riemann surface. So a divisor should be formally thought of as a sum of summation mi xi, where mi's are integers. I'm looking at the free abelian group now. So I'm looking at mi xi, where xi is the points of x. And there's a notion of linear equivalence of divisors. And the degree of a divisor, when I say summation mi xi, then that summation mi is called the degree of the divisor. And then there is a theory which identifies line bundles with such divisors, linear equivalence classes of divisors. And then the Chern class that I spoke earlier on can be understood in terms of the degree of divisors as defined by the algebraic method of working on the free abelian group of points on the Riemann surface. So, of course, there's a third way of defining the Jacobian. One is the isomorphism class of line bundles, the other is as divisors. And third way is to define it in terms of what is called purely in terms of the underlying complex structure of the Riemann surface. So let me mention that one here. So as I said, recall, I mean, I spoke about the genus G. the genus is a topological invariant, but one of the beautiful theories, which later on becomes the so-called Theorem theory, tells you that you can recover this topological invariant by using the holomorphic structure of the underlying Riemann surface. I'm here thinking of the Dolbeau theorem here. So I can recover the topological genus as the space of sections of the cotangent sheaf, the sheaf of differentials on X. And this is, as I said, it's a dimension G, so I can choose a basis here. And in those days, it's this basis of holomorphic differentials used to be called the differentials of the first kind. I just call them omega 1 up to omega G. See, these are holomorphic differentials. I look at the homology of the Riemann surface X, which is the first homology group. And so you have these paths which are there for the homology group. And I can take a form and integrate it over a path. Loops, basically. So I get, therefore, an embedding of the homology group inside the complex, G-dimensional complex vector space by sending a loop sigma to this G tuple by integrating all these basis elements over these sigmas. So this gives you actually an embedding which one has to prove, and the Jacobian of the curve X can be defined purely topologically as the G-dimensional complex torus. This is a complex because it's a complex vector space modulo a lattice of the same dimension. If you have a Riemann surface of genus G, then the first homology has 2G. It's a rank 2G Z module. So this is a real vector space of dimension 2G modulo a lattice of dimension 2G. So this is a complex torus, and this complex torus, as I have explained here, is also called the Jacobian, and this is how the Jacobian is defined. Of course, here we don't see any notion of line joint pieces lying somewhere here and there, and the beauty of mathematics is to link them, and that's one of the things that I'm going to mention a little bit now. So one of the things which is classically, people might have heard of this, is the so-called Abel-Jacobi map, by which I could choose a base point x0 in the Riemann surface X and embed X inside this Jacobian by sending X, by choosing any point X and taking a loop from X to the base point x0 as my sigma, and then sending it to that G tuple modulo the lattice H. And this is a well-defined map. And I mean, one has to prove that, modulo H, it doesn't matter which loop I took here, and in up to homotopy and such things like that. And you get actually an embedding of the Riemann surface X in the Jacobian through this process. So this is a so-called Abel-Jacobi map. So it's very clear that all this was studied already in the 19th century. So it's pretty old mathematics, not really modern mathematics. Okay, so as I said, the H that I'm talking about there is the so-called the homology group of Riemann surface, and it is known to be the so-called the abelianization of the fundamental group. The fundamental group is the homotopy classes of loops on the Riemann surface, and the homology group H1 can be identified with the fundamental group pi1 modulo the so-called commutator subgroup of pi1 of itself. And if you have any group G, I can abelianize it by taking G modulo the commutator subgroup G comma G. A commutator subgroup is a subgroup of G generated by the normal subgroup of G generated by the commutators. Okay, A, B, it's actually normal. It's actually normal. So it's generated by A, B, A inverse, B inverse for all A and B in G. So the quotient pi1 modulo the commutator of pi1 can be identified with the homology group. So, I mean, I could, if I'm looking at the group of characters, a character should be thought of as a homomorphism from pi1 to C star. C star is an abelian group. So it's elementary group theory to say that if you have a homomorphism from pi1 to an abelian group, in fact, it factors through a homomorphism from the homology, which is the pi1 modulo the commutator subgroup, because all elements in the commutator will go to identity through a character. So homomorphisms from pi1 to, I write U1, which is the elements of C star of modulus 1. So it's like the unitary group there. So it's like the unit circle S1 inside C star. I'm interested in the group of characters, unitary characters. I should have said here unitary characters of pi1. And U1 again is an abelian group. So maps from pi1 to U1 is the same as maps from H to U1. So I mentioned a few things. So let me write a little bit here. I've written it already. So we have the so-called quantitative diagram here. I mean, there is this, I'm using the language of sheaf theory here. I have this reals here and the complex sitting inside it, and the quotient is U1. I could think of them as sheaves here. And I have this exponential map from R to U1. U1 is the unit circle. Again, I could look at the constant sheaf Z inside the sheaf of holomorphic functions on X. R is also thought of as the constant sheaf inside holomorphic functions here. And O star is the sheaf of nowhere vanishing, the non-zero. The units of the sheaf OX. So again, I have the map like this here, which is the exponential map e to the power 2 pi I on the sections, and you get a map from OX to OX star here. Sorry. So you write this so-called long exact sequence of cohomology for these two exact sequences and write the diagram. You get a map from H1 of XZ to H1 of, I mean, this, you have a little bit of work should tell you that in fact you get short exact. Normally this map will have H naughts before here on the left-hand side and beyond here H2s. But an elementary remark will tell you that in fact you have something which is like a short exact sequence, H1 of XZ to H1 of XR to H1 of XU1 to 0. And similarly below here too. But here, the last map, if you look at line bundles on a Riemann surface, I mentioned that you can talk about transition functions of a line bundle, which are holomorphic functions from Gij from UI intersection Uj to C star. So they will essentially be elements. These Gijs will satisfy a one co-cycle condition. So H1 of O star will classify isomorphism class of holomorphic line bundles. And the long exact sequence will tell you that there's a map from H1 here to the H2 of Z with coefficients in Z. And X being a Riemann surface, compact Riemann surface, the H2 can be identified with the Z itself. And this connecting map in cohomologies, you can identify it as the first Chern class that I mentioned earlier. So this will be the so-called degree now, because the H2 can be identified with integers. So to each line bundle, I can associate a number called the degree, which is what I mentioned in terms of the degree of the divisor. So they're all connected. I mean, these are all disjointed objects, but they all have a nice way of linking each other. So you have this data here, and then I can look at the kernel of the degree map. So I'm interested in degree 0 line bundle, as we mentioned here in the previous. I was here always talking about degree 0 line bundles here. So when we talk about degree 0 line bundles, I'm looking at the kernel for this map from H1 of X O star to Z. So the kernel by this, since we have a short exact sequence, can be identified with H1 of XO modulo H1 of XZ. So pick naught or the Jacobian, I mean, is the kernel of the degree map. And therefore that will be, this has to be made bigger here. Let me just see whether I can make it bigger. So this pick naught is what we are looking at. So I can replace the kernel of H1 of XO star from the degree map here and put a 0 on the right hand side. And you have a map from H1 of XU1 to this. So this map is by the long exact sequence. But there's an interesting feature that I'm going to talk about now, is that the first cohomology with coefficients in U1, which can be identified with the space of homomorphisms from the homology to U1. This is something called the universal coefficient theorem in topology. And so this space H1 f x U1 can be identified with the so-called unitary characters on the homology. And this map, the vertical map, is what sends you, is a way to associate a character of the homology group with a line bundle. It is this map that we have to understand, and I'll be mentioning about this map a little bit from now. So you have this nice diagram here, and this commutative diagram, this whole picture will tell you then that the space of characters of the fundamental group, which is the space of homomorphisms from H1 to U1, as I said, U1 is abelian, can be identified with the pick naught, which is the degree 0 line bundles. So this gives you an identification of the space of representations of the fundamental group, or the rank 1 representations of the fundamental group with the pick naught. And this I'm expressing pick naught as the quotient of H1 of XO modulo H1 of XZ. And this just a moment. this realization of the Jacobian as H1 of XO modulo H1 of XZ is precisely this identification that I'm giving you. So as you can see, there are three bits that we are speaking about. One bit is thinking of the Jacobian as line bundles of degree 0. The other is in terms of linear equivalence classes of divisors of degree 0. And then the Jacobian in terms of this lattice, CG modulo this lattice, which is cohomologically interpretable as H1 of XO modulo H1 of XZ. So all these three get linked together and they can be identified, and you can think of them as sort of a three ways of looking at the same object in manifestations, one of them algebraic, one of them differential, one of them in some sense holomorphic in a certain sense. So I've not told you how to I mean, this identification I've spoken about H1 of X U1 with the homomorphisms from H1 to U1, but there's a direct way of giving this map, vertical map, that is given a character of the fundamental group. You can give a line bundle, which is going to be of degree 0. I'll come back to that a little later. So this, you can, is in some sense, what I call a trilingual description of the Jacobian. This is the rank 1 case. And when we replace complex numbers by matrices, it's a natural way to extend what I said. The C star becomes GLN, in invertible matrices. So when we talk about vector bundles, the transition functions land in GLN, so we land in the non-abelian setting. So these non-abelian generalizations of these notions is there in this pioneering work of Andre Weil way back in 1938. So which is, as I said, the starting point of the Narasimhan-Seshadri theory. Just like there are these divisors that I spoke there's the concept of a matrix divisor, and one can relate them to vector bundles, just like divisors could be related to line bundles. And the third aspect is I can relate, this is what Andre Weil himself was investigating, was the representations of the fundamental group into GLNC, how one can associate vector bundles to that and kind of link all these things in the manner in which the Jacobian links all these things. So the third aspect is what I would call the Betti aspect. And there's the Theorem aspect, which will not figure here right now, which will come later. And then there is the so-called Dolgo aspect, which is how we will understand the Narasimhan-Seshadri theory. So I'll try to expound on it a little bit. I hope I'm not going too fast. Are there any questions? I'm just going on talking. Maybe we could have questions now, or we could have questions at the end, if that's okay. Suratno, you could tell me that.
Yeah, I have no question till this point. If others have, I encourage them to ask.
Very good. Okay, so at least I'm heard, and I'm happy that I'm heard. Okay, good. Okay, good. So in this setting, I mean, I've still not told you, given a representation rho from pi 1 to GLNC, how to associate a vector bundle. All these are technical, but they are very beautiful. So Weil proved, I mean, way back in 1938, so that's several years back now, that if you take a representation of the fundamental group, you can associate to that representation a vector bundle. And a vector bundle, of course, can be independently defined on the Riemann surface. So he proved a nice characterization. He said a vector bundle on X comes from a representation rho. I'll tell you what it means by that. If and only if it's so-called indecomposable components. You can break up a vector bundle into some sort of minimal objects. If you look at classical Jordan-Holder theory and things like that, we can talk about indecomposable objects in any category. So these are abelian categories. I mean, one has to, this is, I'm looking at sheaves here. So we can talk about indecomposable objects as those which cannot be written as a further direct sum of vector bundles of lower rank. So Weil proved that holomorphic vector bundle comes from a representation if and only if its indecomposable components are of degree 0. So again, this degree 0 comes in here. Because those bundles which come from representations have a certain constraint on the degree. So in today's, and also in this paper of we'll also study the so-called stack of principal GL bundles in its classical adelic sense. Okay, I'm not describing all that right now, but there's a very nice way of writing it as a so-called double coset spaces and studying them. Because there's as always, I mean, at this time, Grothendieck gave a very beautiful expose in 1956 of Andre Weil's work, and that becomes some sort of a bridge between Weil's language and the modern language, which freely uses sheaf theory and cohomology. And Grothendieck's expose, in some sense, puts various work in a perspective, modern perspective, and makes links and makes people like Narasimhan-Seshadri read it with modern language. So let me get back to the Narasimhan-Seshadri theory now. So as I said, the Jacobian of the curve, which is line bundles of degree 0, can be realized as characters of the fundamental group, representations from pi 1 to the unitary group U1. Unitary means that it's modulus 1 complex numbers. So we could analogously, again, pursuing analogy, we could analogously look at unitary representations of the fundamental group. Already Andre Wey had asked about this in his paper. So I'm looking at not homomorphisms from pi 1 to GLN, as is done here in this, which Andre Wey himself took, but suppose I look at the unitary group, which is matrices inside GLNC, such that A times A transposed conjugate is identity. Those matrices which leave a Hermitian inner product invariant. Okay, so we can look at unitary groups and representations from pi 1 to the unitary group now. Instead of U1, I look at UN. So that's the one set of objects that I'm looking at. Now, on the other side, by the deep work of Narasimhan-Seshadri, you need to look at what are called stable vector bundles. See, in the case of line rank 1, the pi 1x representations into U1 gave all line bundles of degree 0. So this discovery, I'm not mentioning here the correct root, but I'm making definitions here. But the notion of a stable bundle is a very mysterious notion, which was independently being studied by Mumford as an example in the geometric invariant, his study of geometric invariant theory. And the beauty of Narasimhan-Seshadri, or the sort of the time spirit of those times, linked these two things. And Narasimhan-Seshadri realized that the right object to be looked at on the other side, that is replacing line bundles of degree 0, should be the so-called stable bundles of degree 0, and maybe expanded a little bit to the so-called semi-stable bundles. So what is a stable bundle or a semi-stable bundle? It's a technical definition which comes from geometric invariant theory, but it plays a central role in this whole story, as we'll see. So a bundle of degree 0 is said to be stable or semi-stable if for every sub-bundle, the notion of sub-bundle makes sense. I spoke about vector bundles as objects which fibers which have vector spaces of rank n, of any rank. Sub-bundles can surely be made sense of there. And the notion of a degree for a vector bundle makes sense. So the number called degree f by rank f is what is called the slope of a bundle. This makes sense. So we want that all sub-bundles have slope strictly bounded by 0, or with a non-strict inequality bounded by 0, whether it's a stable bundle or a semi-stable bundle. Notice that for line bundles, this definition is vacuously true always, because a line bundle does not have a sub-bundle at all. A sub-bundle means that it's not just a subsheaf, but it's actually a sub-bundle that the quotient is also a vector bundle. So a line bundle does not have any sub-bundles because of the rank being 1. Therefore, every line bundle is automatically stable. So this is the beginning of the non-abelian phenomena that starts coming up here. So what is the famous theorem of Narasimhan and Seshadri? How much time have I spoken already? More than half an hour?
40 minutes.
40 minutes. Okay, good. Okay, so I need to keep track of this. Otherwise, I'll go on and on. Okay, so the basic theorem of Narasimhan-Seshadri, let me just state it first, and then I'll elaborate on what I mean by all these things, is that there is a bijective correspondence, firstly. This is more than a bijective correspondence. It's a nice identification of some geometry which underlies both these spaces. This bijective correspondence is realized using algebraic geometry. That's the beauty of all these things. But the theorem could be stated as saying that irreducible representations of the fundamental group. Irreducibility is crucial here. Notice that when I spoke about characters, there is no concept of irreducibility there, because we land in the abelian group C star there. So irreducible representations means, as usual, a representation is said to be irreducible if the image does not leave any subspace invariant. I'm looking at, if I take a representation rho from pi 1x to UN is sitting inside GLN. So each element of the fundamental group, I can take rho of, say, sigma. It's a matrix now. And I look at the set of all rho sigmas as a collection of matrices. This collection of matrices together, that means I'm looking at all possible element sigma in pi 1x, and I'm looking at the collection rho sigma now, which is a bunch of matrices inside GLNC. This set of matrices that I'm looking at is what is called an irreducible set, in the sense this particular collection does not leave any proper subspace. See, I'm looking at it as a matrix, invertible matrix acting on from Cn to Cn. So I don't want any proper subspace of Cn to be left invariant by this totality, this total collection of matrices indexed by the fundamental group. So that's what is an irreducible representation. But I'm looking at representations not into all GLN, but those which leave a form invariant. So it's in unitary group, the matrices. So irreducible representations of pi 1 into unitary mean matrices could therefore be thought of as 2G, because pi 1x is generated by 2G matrices with a single relation. All these things could be just said for the generators. So I could look at 2G matrices inside the unitary group, modulo one single relation, that the product of the commutators of those matrices should be equal to 1. And the moment you give me one such bunch of 2G matrices, I'm giving you a representation. That's what it means to give a representation. So if you have the representation, then there is to such representations one can identify so-called isomorphism classes of stable bundles of Rankine integrals. So this correspondence is called the Narasimhan-Seshadri correspondence. Its proof is rather non-trivial. I mean, to this day, there's no simple proof for this theorem. I mean, very recently I gave a proof in my course in my institute, and it's a rather mysterious theorem in the sense from the one-way map from representations to vector bundles is writable. I mean, you can expect what vector bundle to get, but starting with a stable bundle, how to recover back a representation is a very existential theorem. I mean, you can't do it by reconstructing back the representation. So in that sense, it's mysterious. And how does one do it? So before I do that, let me just go here. I mean, I wrote this page afterwards. So let me just tell what do I mean by associating a vector bundle to a representation. So my map P or pi, I don't know, I called it pi perhaps there. P is the projection from the upper half space to X. This is the universal cover map. So X can be identified with the quotient H modulo pi 1. If you take a representation rho from pi 1 to UN, the unitary representation, you get an action of the fundamental group pi 1 on Cn via the rho. I mean, if I take a vector V in Cn, each element of pi x through rho is thought of as a matrix now, so it will act on the vector. So that's the action on Cn. And once you have this action, you can take the upper half space cross this complex vector space Cn, and H has an action because pi 1x is acting on H on the right, being the group of deck transformations or the fundamental group of X, it will act on the universal cover. On Cn, it is acting through representation rho. Therefore, on the product, there's a natural action, the diagonal action, if you wish. And that means that you can take a Z comma V, and that is for every gamma, I identify Z comma V with Z dot gamma, comma, rho gamma inverse dot V. This is the diagonal action on the product. That's why I put a rho gamma inverse. If you check the action relation, that's what it is. So given this construction would then construct this V rho, I mean, this H cross Cn is living on H, but I'm going modulo the action of pi 1. So this V rho will really exist as a space on top of V, on top of X. So this V rho can be shown to be a vector bundle, holomorphic vector bundle. It's holomorphic because my pi 1 is a discrete group, and one can prove that this is actually holomorphic. Moreover, this vector bundle V rho that I'm constructing here is actually of degree 0. So this vector bundle already came up, as I said, in Andre Wei's work. So this is the vector bundle you associate to a representation. And what Narasimhan-Seshadri theorem is saying is that, firstly, it says that this vector bundle V rho is stable in the sense of Mumford, in this sense. So this is the first big discovery, that it is actually stable. And not only that, they are saying that if you start with any stable bundle up to isomorphism, you can actually get an irreducible unitary representation. Okay, unitary representation, not any arbitrary representation. You get a unitary representation such that this vector bundle V actually is isomorphic to a vector bundle of the type V rho that we are mentioning here. So how does one, I mean, I'll just give you the gist of the idea here. I mean, you have to give the space of representations from pi 1 to unitary group, a space of a real analytic variety. Notice that UN is only a real group. It's the so-called maximal compact subgroup of the complex GLNC. GLNC has a holomorphic structure, but UN does not have. It's a real analytic manifold now, the space of irreducible representations. And this association that we are writing from rho to V rho, so I have to give a certain geometry on the right-hand side in some sense. And the geometry is provided for by Mumford's work, the space of stable vector bundles. So once you prove that this vector bundle V rho is stable, at least set theoretically, you have a map from this the real analytic variety of representations to the complex manifold Mn0x, the moduli space of isomorphism classes of stable vector bundles. And then one has to prove that, one has to prove that this map that you've written down is really a continuous map, firstly. And then one has to analyze this map and end up proving that in some sense, this is an isomorphism of some kind, where you give a real analytic structure on the space of model space of vector bundles. And you prove that, in fact, by comparing the tangent spaces and dimension count and several other subtleties where you need some sort of a existence of a compact space. You need to have limits when you check sequential convergences and things like that here to prove that this, in fact, gives an isomorphism. So it's a rather deep piece of paper. Mathematics came in 1965, 2 papers of Narasimhan-Seshadri. One which studied the analytic space, this left-hand side, real analytic structure, the deformations of representations, the tangent spaces there. And as if they were planning for this next paper, which appeared in the Annals of Mathematics in 1965. And the space of representations, the isomorphism class of stable bundles was studied, as I said earlier on, but this relationship makes this space even more striking. And subsequently, for other purposes and more development and deeper analysis of this whole thing, a compactification of this moduli space of stable bundles was done by Seshadri, which is in some sense key to many of the ideas which come up later, where he defined the so-called equivalences on semi-stable bundles to compactify the space of stable bundles. Of course, as I am talking about irreducible representations, but if you don't talk about irreducible representations here, but I'll talk about all possible representations, which means you take any representations of pi1 into UN, then the identification is no longer with the isomorphism class of stable bundles, but it's identified with the space of S-equivalence classes of semi-stable bundles. There is something called a polystable bundle, and there are some technicalities. So this moduli space of S-equivalence class of semi-stable bundle, which is a compact object, is the precise analog, non-abelian analog of the classical Jacobian variety. This is the non-abelian picture now. The non-abelian because we are working in higher rank vector bundles. So this is the topological part, what I call the Betti side of the story, is the space of irreducible representations of pi1 into UN, replacing this space of characters of pi1 here. And the Dolbeau side, in some sense, should be thought of as the isomorphism class of stable bundles. Again, the miraculous thing is that stability, which was being studied for completely different reasons, comes up here as the natural answer to the question which they were looking at for the Narasimhan-Seshadri theorem. So this is a great piece of mathematics. It has several intricacies here, and some of them I'll just mention here, and then we'll go on to what are its implications or ramifications. Okay, so this is what I mentioned as V rho here. So let me go to the next one. So I want to say a few things. Since it's a short, I just wanted to say about how this Narasimhan-Seshadri theorem developed in many ways. One of the questions that came up became very prominent in the 1980s was higher dimensional analogs of the Narasimhan-Seshadri theorems. Basically, Narasimhan-Seshadri worked on Riemann surfaces, so it was natural for it's easy to say it's natural, but questions that were which came up in the early 1980s because of a work of Atiyah and Bott and its development in Oxford, higher dimensional basis of, where X could be a smooth complex, a smooth surface initially, and then maybe a projective variety of dimension D, and then later on even a compact scalar manifold, complex scalar, a compact scalar manifold is itself enough as it comes up in the work of Uhlenbeck and Yao. So one could ask for higher dimensional analogs for all these things. And I could just start by saying that if you take a smooth projective variety, there's something called the Lefschetz hyperplane section theorem. And you could take hyperplanes here and take the intersection of a hyperplane in PM. I mean, a projective variety is something which comes with an embedding fx inside PM, and I could take a general hyperplane here and intersect it with x. And this inclusion induces an isomorphism in homologies up to degrees d-1, where d is the dimension of the variety x, and a surjection at d-1. So this could be thought of as something like the abelian aspect, and one could ask the same question: what happens in the non-abelian cohomology set? Vector bundles are classified by the cohomology set H1 of x, coefficients in the sheaf GLN there. So the Mehta-Ramanathan restriction theorem could be philosophically thought of as a non-abelian analog of the Lefschetz hyperplane section theorem for stable vector bundles. So what they proved was that if you take a smooth projective variety of dimension d, this is starting point of some higher dimensional techniques. If you take a smooth projective variety of dimension d and look at vector bundles, the notion of stability can be defined if it's a projective variety in terms of what is called a hyperplane class. And we can talk about the degree of a vector bundle even on a smooth projective variety with respect to a choice of a hyperplane class. And then once you have a hyperplane class, then you can look at, for example, if you work with a surface, then if you choose a hyperplane class, you can look at curves inside the hyperplane, the linear system defined by the hyperplane class, and you can restrict a vector bundle on the surface to a curve. And then if the curve is inside the hyperplane class where the degree is being computed, I mean the hyperplane class which computes the degrees, then the restriction will continue to have degree 0. Then Mehta and Ramanathan answer the question of when vector bundles, I mean stable vector bundles, when to what sort of curves when they're restricted will continue to remain stable or semi-stable. So they have this very nice result which becomes a key tool in the high dimensional analogies. Mehta Ramanathan also show that if you assume all the Chern classes vanish, the analog of degree 0, that means not just the first Chern class, because when you're in a higher dimensional variety of higher Chern classes, you have to, if you assume all of them as 0, then you get as an easy consequence the so-called Narasimhan-Seshadri theorem in higher dimensions using Donaldson's work. I'll come back to that. So let me just say that, because we're talking about higher dimensional thing, what was the motivation for the Oxford school? I mean, Atiyah, Bott, Bott of course was in Harvard there, but the school, Atiyah school, Hitchin and several other people, they were looking at instantons and Hitchin and others studying such things. So this in mathematical physics, vector bundles over the force sphere led to non-abelian generalizations of the so-called Maxwell's equations. And you can have analogs for, if you have other 4 manifolds, then you have the so-called non-abelian analogs of Hodge theory. Let me just mention it like that. And Atiyah Bott in a paper in 1982 relate this stable bundles up to now, which was related to the fundamental group representations, to principal SUN bundles with the so-called irreducible Yang-Mills connections. That means a purely differential geometric characterization of stable bundles were being attempted. Okay, in this. What Donaldson proved was, that first noticed that Atiyah and Bott identified stable bundles with irreducible. The notion of irreducibility has to be suitably defined in terms of the so-called holonomy of these connections. Irreducible flat unitary connections, and flatness should be thought of as vanishing of the so-called curvature of these connections. At this time in the early 80s, Kobayashi and Hitchin had suggested a higher dimensional generalization. So let Y be a KLM manifold, for example, a smooth projective variety. Then the stability of a bundle is related to the existence of a complex. A complex connection has to be suitably defined. It gives you a so-called almost complex structure. Let me not get into the technicality. There's a complex, a unitary connection. A unitary connection means that you had a reduction of, the holonomy is actually unitary here, whose curvature is constrained to be a constant multiple of the identity as a section of the associated Lie algebra bundle. So this is a bunch of technicalities here. All this put together is a so-called Einstein-Hermitian condition. Okay. So once the setting was there, Donaldson showed in a very deep paper, which is a real breakthrough paper in higher dimensions, but he had done it earlier for the analog of this on the Riemann surface. That means Donaldson gave the so-called differential geometric or the Theorem side to the non-abelian cohomology. I spoke of the Betti side and the Dolbeau side, and then there was a Theorem side, which was giving a Narasimhan-Seshadri theorem purely in terms of Einstein-Hermitian connections, and that's what he did earlier for the curves. And then he proved this for higher dimensional varieties, because once he understood that case for Riemann surfaces, and with the question of Kobayashi-Hitchin here, and the work of Atiyah Bott, he could generalize this whole thing by using Mehta-Ramanathan's restriction theorems and very subtle techniques. He proved that if E is a stable bundle on a projective surface, it's a stable bundle if and only if. But I'm saying he proved only one way. Kobayashi and Lübke had earlier shown that if a bundle, it's analogous to proving that the vector bundle B rho that we studied there was stable. So if a bundle has such a connection, then it is stable, is easier to prove, relatively speaking. And Donaldson proved the converse, if and only if part in some sense. So this completely characterizes, in some sense, a differential geometrically stability of bundles. So this is a breakthrough result of Donaldson, which led to, mysteriously to, I suppose for people who are working in topology, not all that mysterious, study of what are called exotic structures on the R4. I'll come back to that a little later. So Donaldson had proved, as I said earlier, he had proved this version for compact Riemann surfaces, which was, I think, in his master's thesis maybe. And this theorem was later generalized to all smooth projective varieties, first by Donaldson and then by Uhlenbeck and Yau for compact Kähler manifolds. That line is missing here in my screen here. So what are topological ramifications? So before I go to other ramifications where I'm more comfortable, let me just list a bit of fantastic topological applications. So the above theorem of Donaldson got linked to deep topology of 4 manifolds. There was work of Friedman already on, and people had already been looking. This famous, if you look at the Euclidean space Rn, then one can ask, what are the, and then there's this, when I talk about Rn, I always talk about advanced calculus tells me that there's a standard differential structure on Rn by which I can do calculus there. So it is a natural question to ask, because Milner had proven in the late 50s that the seven-dimensional sphere could be given C-infinity structures which are different from the standard one. The standard one is the natural one in which the charts are given as we normally understand them on spheres. Milner's work used Hopf fibrations, very beautiful ideas about from cobordism theory there. The question about Rn was on, and I think in the early 60s, if I remember right, Smale had already proved, the fact that R1, R2, and R3 have a unique differential structure was known. R1 is easy, R2 and R3, I can't immediately remember an argument. But R4, R5 onwards, Smale proved using H cobordism theorem that there was a unique C-infinity structure on manifolds of dimension bigger than or equal to, Euclidean spaces Rn n bigger than or equal to 5. R4 was the mysterious one which remained there, and people were looking at it from several angles. Friedman was one among them, and using the work of Donaldson, it was proven. Friedman and Donaldson together, those ideas led to the proving of exotic structures. There are other, in fact, there's an infinity of them, of exotic R4s, which are homeomorphic to R4, but not diffeomorphic to the standard R4. Okay, so just a comment that these exotic R4s, there are compact subsets which such that no smoothly embedded 3-sphere in R4 contains K. This kind of property is what they were looking at and how they could get hold of such exotic structures. So this is one of the deep consequences of the Narasimhan-Seshadri theorem, which nobody, of course, expected. The structure of these exotics R4s is, I do not know that it is fully understood, and I don't know too much about it. I know that this kind of thing was there, and I have some idea of how these things go. I mean, there's a way of giving these structures in terms of the intersection form and the homologies. I mean, this is something just to be done with care. But what is more important is that, and for me, was that Donaldson's work showed that bundles with the C1 equal to 0, but higher Chern classes, CI, C2 onwards, they become more important in higher dimensions. So I come to more comfortable zones here. I mean, I make a leap here because I'm giving the talk. I'm going to talk about some work which I had done much later in 2006. I mean, there were several pieces of work in 90s, late 80s, I'm not talking about here, which is the work of Hitchin, the work of Simpson. There are enormous developments which took place, essentially, as I said, all originating from the Narasimhan-Seshadri theorem. And I mean, if I go, I mean, it's a big story. So I thought I'll just talk about something which is connected because to my work a little bit. So I was interested in I was looking at the study of principal bundles, and in a paper with Kolar, I tried to understand the Narasimhan-Seshadri theorem as the original, not generalizations in higher dimensions in a different way, but understood from the old Narasimhan-Seshadri phenomenon itself. So this was a result I proved. So if you take a smooth projective variety with an ample line divisor, line bundle H or a divisor H, and for example, take dimension x equal to 2, let E be a stable bundle. I mean, as I said, stability is defined in terms of this degree here, which is the intersection number of C1e with H, and assume for simplicity that C1e is 0. Suratno, how much time can I take from here? Another 10 minutes of 10 minutes? Is it okay?
10 minutes is fine.
Yeah, that's all that I'll take. Okay. So, as I said, this Mehta-Ramanathan restriction theorem will tell you that if you take a sufficiently general high degree hyperplane section C in this linear system, high degree M is large here, then the restriction of this stable bundle to C is a stable vector bundle on the curve, smooth projective curve X, curve C, which is therefore one can identify to the Riemann surface. We are working in complex numbers here now. And since it's a stable bundle on C, by old Narasimhan-Seshadri theorem, it comes from irreducible unitary representation of the fundamental group of C. So we get hold of a curve C in 1 degree now. We can go on restricting it to higher and higher degree curves. And then using the Narasimhan-Seshadri representations from the fundamental groups of these curves C into GLN, one can actually construct a subgroup, an algebraic subgroup G of GLN, where N is the rank of E, says that the structure group of E reduces to G. And this G can be, in some sense, identified with the Zariski closure of the holonomic group of the Einstein-Hermitian connection of E. Notice that since E is a stable bundle on X by this Donaldson's theorem, I have an irreducible Einstein-Hermitian connection, which means that I have the holonomic group, which is a unitary group in this case, which is irreducibly sitting inside GLN, and there is a connection so that I can get a reduction of structure group of my bundle to that unitary group, okay, as a part of the Donaldson theorem. What I'm saying is that using these restriction theorems and these representations of the fundamental groups to the restrictions, one can actually reconstruct back not the differential geometric holonomic group, but the smallest algebraic group which contains that inside GLN. So this is in some sense looking at something like an algebraic holonomic group, which can be recovered from the Narasimhan-Seshadri phenomenon. So this can be thought of as an approach to a higher dimensional theory. Then I later on developed this with my colleague Parameshwaran in the Tata Institute with some sort of Tanakian analogs, and we could ask whether there's a positive characteristic philosophy in the Narasimhan-Seshadri theory. I mean, Narasimhan-Seshadri theorem is a pure characteristic zero theorem. We are looking at fundamental groups there. In in characteristic P, when we go there, we don't have analogs of fundamental group as a universal covering space. So what is the right analog there? And we developed a theory which is motivated by my work with Kolar. We developed algebraic holonomic groups. And we can realize the Narasimhan-Seshadri theorem in some sense as a philosophical theorem in terms of irreducible representations of the fundamental group scheme of a suitable Tanaka category. So that's a philosophical way of looking at a high-dimensional Narasimhan-Seshadri theorem, maybe even in positive characteristics. I'm not going into the details there. So these are two ramifications. I mean, let me just say something interesting for somebody who may already know this. So I'm saying that if you start with a stable bundle of degree 0, one can generate something called a Tanaka category from the stable bundles by taking its tensor powers of the vector bundle and its duals. The Narasimhan-Seshadri theorem would tell you that all these tensor powers are all continuing to remain semi-stable. So you can construct this Tanaka category TV. Tanaka category is a great construct of Grothendieck's. And there exists, in fact, a group scheme whose representations will give you the points of these objects in this Tanaka category. And I'm going a little fast here. I'm sorry about it because of lack of time. But then one can relate the unity representation. I mean, I'm working on a curve now. So assume that V is a vector bundle on a Riemann surface. Then you can still make sense of this Tanaka group and this Tanaka category. And one could ask the relationship between the Narasimhan-Seshadri representations and this Tanaka category. And one can prove that the image under this Tanakian representation, rho prime, is the smallest algebraic subgroup in GLNC containing the Narasimhan-Seshadri image under the unitary group. So this is a relationship which gets generalized in my work here. Okay, so let me go into a different kind of ramifications here of the Narasimhan-Seshadri theorem. Ramanathan in the mid-70s had already studied, instead of GLN, he looked at principal G bundles. G could be a semi-simple algebraic group or a reductive algebraic group. And he answered the question of Narasimhan-Seshadri by looking at representations of the fundamental group to the maximal compact subgroup of G, which is I've written it as KG. This KG is a replacement for the unitary group. And he had the analogous results like the Narasimhan-Seshadri theorem and Seshadri's construction for moduli spaces of stable G bundles, which he proved is again semi-stable bundles. He proved is a compactification of the stable moduli and the exact analogies there. So this was a deep piece of work which lays the foundation for the study of principal bundles on Riemann surfaces. Ramanathan did this essentially in his PhD. So it is a masterly PhD thesis, I would say, and which has all the advanced techniques from Grothendieck's work. It's a great piece of work. So this is a one page for Ramanathan, which is rather unfair, but I guess I don't have the time for that. And Ramanathan and Subramaniam also generalized the Donaldson analog of this for principal bundles on high dimensional varieties. But on the other hand, I spoke about Fuchsian groups earlier. So this is again coming back to my work. So I want to say a little bit here, some sort of self-advertisement. So you can look at, you can fix marked points on the Riemann surface X and look at groups which look like these, which are not just the fundamental group, but 2G generators plus a bunch of lassos around these marked points, C1, C2, Cm, small loops around these curves, with the condition that the product of commutators together with the product of those loops is equal to identity. And each of these loops is a finite order element. I mean, this is a special kind of a Fuchsian group with so-called elliptic fixed points on the upper half space. And you can again view the Riemann surface X as H modulo pi, but now this action of pi is no longer free. It has got marked points where the stabilizer is non-trivial. So then one could ask, in fact, this was already asked by Andre Wey, that you could look at homomorphisms from this Fuchsian group into the unitary group or into the group G or GLN, whichever way. And then you can fix the images of these loops Ci and fix their conjugacy classes and look at the space of such representations. So this space of representations of homomorphisms from pi into the maximal compact with fixed conjugacy class can be denoted by R tau. And one is interested in this space, which is again the analog of the space of representations, unitary representations of the fundamental group. And we can ask what you get on the other side. And there's this work of Mehta and Seshadri, which answered this analog of this for the case when KG is the unitary group. and you get this famous Methadone-Seshadri theorem of parabolic vector bundles, which gives you the analog of the Narasimhan-Seshadri theorem for Fuchsian groups. But if you ask the analog of the Narasimhan-Seshadri theorem or the Ramanathan theorem, where the Fuchsian groups have representations into G, mysterious new phenomena coming, which is the greatness of Narasimhan-Seshadri theorem. It opens up so many beautiful ideas and new things. So the new ideas that come up is that you no longer, I mean, although the Methadone-Seshadri theorem still worked in the realm of vector bundles, the moment you go into other groups G, you have to enter the realm of not principal G bundles, but what are called torsors and more complicated group schemes, which have already been studied way back in the 1960s by Brewer and Titz, and even earlier by Iwahori and Matsumoto. All these things came up in periodic representations in arithmetic and the study of representation theory there. And these group schemes were studied in the mid-60s, and the massive papers written by Brewer and Titz. But to relate them to bundle theory was in some sense in the air in 2010, 2000. And in a work with Seshadri, I managed to prove very recently, I mean, this appeared in 2015. So Seshadri was already 83 years old. And it was a joy of collaborating with him. It was my last paper with him. And we identify exactly in the Narasimhan-Seshadri philosophy, the so-called conjugacy classes or representations of the Fuchsian group into the maximal compact with a space of S-equivalence classes. We can talk about stable and semi-stable torsors now. Torsors because the group schemes are not constant. This is the theorem that we proved recently, which is an interesting theorem by itself and opens up very new possibilities in the study because of Brewer-Titz theory coming in a fundamental way here. I guess I'll stop with that. I've already taken an hour and 10 minutes.
Thank you, Professor Balaji. It was a wonderful talk. So is there any question?
Was it too technical?
Yes. Can you just go back a few pages? I think the Fuchsian group, there is this relation Ci to the power Ni. What are those Ni?
Ni's are the stabilizer. As I said, the Fuchsian group is acting on the upper half space with the finite stabilizers. Those Ni's are the order. The Ci's are the generators for the small, but the stabilizers for. I mean, if I take any point up in the upper half space and look at the stabilizer there are cyclics groups. I'm looking at a certain type of Fuchsian group, and the finite cyclic group order is Ni, and these Ci's are generators for those cyclic groups.
And if the degree is greater than 0, then the analog for, I mean, you take the fundamental group representations, and you get the 0. Now, if you want to get positive degree stable bundles,
you have to look at.
Can you give the little construction that how to get non-zero degree bundles from?
You can, whatever I've just written here, you can restrict your attention to one puncture instead of m of them. If you restrict your attention to one puncture, but also make sure that this Ci maps to something which is a central element. When I look at Fuchsian representations here, I want to map this pi, look at pi with not m equal to 1, and the image of that Ci should be central, if I say, of some. Then you can pick up other degree. I mean, you can, through this theory, you can recover other degree bundles by this association. Parabolic bundles of a certain kind, you can say. These are called special parabolic bundles or special bundles in Narasimhan-Seshadri paper. And so you can, the same theory, but extended to Fuchsian groups can give you back bundles of degree non-zero or C1 non-zero. C1 zero, all the Ci's that I've written here should be identity. That means it's the fundamental group representations.
Yes.
But to get non-zero, then you start to bring Ci's there. But so you are looking at representations of the punctured Riemann surface. So that's the
Ramanathan's moduli space. That is a coarse moduli space.
That's right. Exactly like Seshadri's theorem. Yeah, and these are S-equivalence classes.
In the differential theory, yes.
Yeah.
In the Donaldson theory,
Mhm.
is it taking a projective manifold or just
Always.
projective?
Otherwise, I can't talk about the stability. No, I need a hyperplane
Yes,
divisor
yes,
to
yes.
talk about the degree. Yeah.
Yes, absolutely.
Yeah. And
Yes.
this.
And can you just go back to the left side hyperplane theorem and
Just a moment.
yes.
Yeah, this one.
Yes, can you just so between which two homologies that this isomorphism is given?
Which one? Here?
Yes.
So this is if I look at HD minus 1 of P
Okay.
intersection X is equal to HD minus 1 of up to Hj up to J equal to D minus 1, they are the same. And then there's surjection at D minus 1 up to D minus, you understand what I'm saying?
Yes, can you just say it again? Yes.
Hj of P intersection X
Yes. I
equal
see.
to Hj of X.
I see. Okay.
I'm just philosophical. This is just, these are analogies. Okay, there is no, I cannot, when I say Methadone is a restriction theorem, in my mind there's a philosophy. I do not think anybody has mentioned it like this, but I feel there's a philosophical link with this kind of thing. Because I have a non-abelian cohomology. My vector bundles are non-abelian cohomology elements. And when I restrict it, I'm in some sense going from H1 of X to H1 of C for some small c inside it. Say, for example, if X is a surface. So cohomologically, the map goes in the other direction. Homology goes from the sub to the bigger one, here from X to the smaller one by restriction.
Yes.
So this was my analogy there. I mean, this is just a thought. I mean, and it plays a key role in Donaldson's works and also in the way I'm looking at this story here. Some sort of a analog that I did with Kolar, which I mean, restriction theorem play an important role here. So that's just I mean, it's just like the realm of analogies. Anything which is even vaguely analogous could suggest to you something. So it was just I mean, it's just a way of just saying something. This aspect, I couldn't dwell, but I'm just trying to say something here. If you have time, you can ponder over it, but we can talk about it later.
So Saurav is asking a question.
Yes, please.
Let me read it out. Statement of a theorem known as Riemann-Hilbert correspondence has a little bit of similarity with that of Narasimhan-Seshadri theorem.
Very much.
When was this theorem proved? Is there any historic relation?
There's no history. I mean, Hilbert. No. Riemann-Hilbert correspondence. I don't think there is. Maybe they were all in the air. I mean, that is something. I mean, philosophically very similar, I would say. But I think it was done again in the 80s. This was a work of Deline, Bellinson, and all these guys, right? With power sheaves in Sussex. That's what I know of that. I don't know much about the Riemann-Hilbert correspondence more than something like that.
So Narasimhan and Seshadri's first theorem was they proved that space of reducible representation modulo conjugation is a complex manifold, right? Because
only real analytic. No, there's no complex structure.
No, real analytic is clear, but I think they proved holomorphic structure using.
Sorry, huh?
I think in that paper they proved.
They give the holomorphic structure also. Correct. Truly.
But there is no algebraic that comes from.
That's true. Correct. The complex structure comes by looking at the deformations there.
Yeah.
That's right.
Is there any more questions?
Just a remark, this lecture was so pleasant that I feel that we have made a very good start in our distinguished lecture series of this university.
Thank you so much.
Well, thanks to Professor Vikraman Balaji.
Yeah, thank you. It was a wonderful lecture.
Thank you very much. I hope some people enjoyed it and they feel like, pursuing this kind of mathematics. This is a different kind of mathematics. I mean, all these are, as I said, somewhat Bourbaki influenced, but they're
Sujay is asking some question. Is there stack version of this?
Stack is no. Stack is not. That's not a. Well, I would say that if you stop short of stability, then you can talk about the stack of objects. So, as I said, the stack was already looked at even way back by Andre Weil in some sense. So the coarse space for the stack is the harder part here, which is what the JIT comes in and you construct the coarse moduli space for that. So the stack is essentially trying to understand, give the structure on the space of a vector bundle itself. So you can talk about the Bun stack or the Bun G or Bun GLN, which one can make sense of here, but we are interested in looking at an open substack there which has a coarse moduli. And the GIT gives you the criterion by which you can actually do that. Of course, you can ask for more general stacks, such questions, but they are being looked at now, whether you can have such criteria. These are Artin stacks, whose coarse spaces are constructed using GIT methods. There's no the representation theory. Sorry. I don't know whether yeah, that's the only answer I can give there. Stacks don't really play a role in that sense here.
Sir, hello.
Yeah, please go on.
Sir, actually, Fuchsian groups can contain also parabolic elements. So if we include the parabolic element,
even then there is an analog. You see, what happens is, I didn't go into that. And there are subtleties about what I used elliptic fixed points here. If I had a little more time, I would have developed it. The whole pun was on ramifications here. If you have parabolic fixed points, you get into so-called parabolic bundles with real weights, okay? Because the stabilizer could be integers for a parabolic fixed point. And there, the theory, but what happens is, these are the so-called real weights or rational weight theory that comes up in parabolic vector bundles. The rational weight theory can be, in some sense, handling elliptic fixed points. But then there is a very nice philosophy in the Narasimhan-Seshadri paper, which is called the theory of variations of weights. And when you're interested in stability of these so-called parabolic bundles, you can vary the weights and use the fact that the moduli spaces don't really change when you go to nearby weights. So if you're really interested in the representation theory of Fuchsian groups, and if you're really interested in the moduli space per se of parabolic bundles, it's enough to study Fuchsian groups with elliptic fixed points for the realization of the moduli space. But if you're interested in purely in terms of the objects which underlie the moduli space, that is, if I'm interested specifically in a parabolic bundle, stable bundle, maybe with real weights, then I need to look at parabolic fixed points and realize it as a direct construct from the upper half space when some sort of invariant push forward. And that relationship is already there in Mehta-Seshadri. So this, my paper with Seshadri, which we did here, which I mentioned here for the group G, we fix elliptic fixed points and do it. But the real analog of that is the parabolic analog, fixed points analog, has been done by myself and Biswas and Ashwini Pandey in another paper in 2018, where we answer that question also. So one can handle both. This can be done. One has to bring in this theory of variation of weights, carefully done there.
In higher dimension, has anyone studied this Donaldson-Uhlenbeck for parabolic bundles?
I think so. I think all that has been, I mean,
I have only seen the one Narasimhan and some Chinese guys paper for surface, but higher dimension, are you aware of?
For parabolic bundles, Yokogawa, but
no, I'm saying that Narasimhan-Seshadri the correspondence.
Yeah, the Einstein admission kind of thing has been done by, I think, Botachin or somebody, perhaps.
Botachin.
Yeah, one of those people from the French school was done. It was done. Several people were working on it. There was a whole English school where several people were trying this kind of thing.
Okay.
And it's been done. That much I know.
Yeah. Okay.
So there is a complete differential geometric characterization of that.
Okay.
Yeah, that's true. That's there.
So Professor Kannan, someone is asking for feedback form. How to send? I don't know. Is there any way?
I At present, we are not readily having a form like that, but we will send to that person later.
Okay.
Hello.
Yeah, please.
Sir. In this talk, we always take the presentation UNC presentation, means unitary presentation.
Yeah.
If we take instead of UNC, we take GLNC. Is there any analog of that GLNC?
Yeah. See, I mentioned very early there that if you just work with representations of the fundamental group into GL and C, they are classified purely in terms of their indecomposable components. This is there in Andre's work. But if you, I didn't mention the moduli space analogs there. Higgs bundles is the correct analog for that. But there the association from rho to V rho is not a straightforward association. To relate the so-called space of representations of the fundamental group into GLN, look at the identification of that space modulo conjugacy, one needs to identify to the so-called Higgs bundles, but that correspondence is more delicate, where you have to look at vector bundles E together with a mapping from E to E tensor, the canonical line bundle, or more generally you can define it in higher dimensional varieties also. And the moduli space can be constructed and one can identify. This is Hitchin's work. This is late 1980s when this fundamental work was done. And I didn't spend time because it's again too far in too many things. The algebraic geometry there is also very nice there. And it has been generalized by Simpson in the early 90s for higher dimensional varieties. So one can look at the representations of the fundamental group and study them. These are the character varieties which one can study. And there's the Hitchin moduli space is again a grand generalization of the Narasimhan-Seshadri theory, where you have where links with symplectic geometry and and Langland's theory. I'm told that Hitchin's work plays a key role in Ingo Bauchow's proof of the so-called fundamental lemma. So the ramifications of Narasimhan-Seshadri, you can say that you can trace back most of these ideas to at least the starting there in some sense. So and that's the way I would like to see. So that's the reason why it's considered so basic. So all these things are there in the background. We require more time it's too much time in fact. I'm just skimming without even telling what the objects look like. I didn't spend any time telling you what the proofs were.
I will look forward to hearing from you in more details.
That require a course.
Yeah. So are there any questions? If not, let us thank the speaker once again for this wonderful talk.
Thank you very much. Thank you for inviting me. It was a pleasure.
Okay.
Thank you.
Okay.
Bye.
Okay.
Bye. Okay, Professor Kannan, thank you very much.
Thank you, sir. We should thank you for making a very good start. The series will go very well now.
Okay. Thank you very much. Thank you.